This text discusses commonly used libraries for data analysis and visualization in Python. 1. Numpy, imported as NP. Numpy is a widely used library for numerical computing in Python. It offers support for large, multi-dimensional arrays and matrices, as well as a set of mathematical functions for efficient array operations. 2. Pandas, imported as PD, built on top of Numpy. Pandas provides data structures like DataFrame and series that are essential for data manipulation and analysis. Additionally, Pandas offers tools for seamlessly reading and writing data between different file formats and in-memory data structures. 3. Matplotlib. PyPlot, imported as PLT. Matplotlib is a versatile plotting library in Python that provides an interface similar to MATLAB for creating various types of visualizations, including static, animated, and interactive plots. By importing Matplotlib PyPlot, users can generate plots like line plots, scatter plots, bar plots, histograms, and more. 4. I/O. This module is Python's primary tool for handling different types of input-output operations. It can create file-like objects from strings, which is useful for functions requiring file-like input-output handling. By importing these libraries, users gain access to robust tools for processing, analyzing, and visualizing data in Python. Integrating Numpy, Pandas, and Matplotlib enables efficient data manipulation, computation, and visually appealing result presentations. This snippet enables a user in a Google Colab environment to upload files from their local system to the Colab runtime. It begins by importing the Files module from the Google Colab library. Then, it utilizes the upload function to trigger a file upload dialog, enabling the user to choose files from their local system for uploading. After the user selects and uploads the files, the code proceeds to iterate over the uploaded files using a for loop. For each file, it displays a message showing the filename and its size in bytes. This code is valuable for Google Colab Notebook users who need to import external data or files for analysis or processing within the notebook environment. It offers an interactive and straightforward method for users to directly upload files into the Colab runtime. This process involves reading a CSV file called dowjones.csv and transferring its data into a Pandas DataFrame via the read_CSV function within the Pandas library. The resulting DataFrame is ideal for conducting analyses, manipulations, and visualizations on the CSV file's data. Employing this method is crucial when handling CSV data within Python using Pandas. Transforming the data into a DataFrame facilitates efficient execution of data analyses, cleaning processes, manipulations, and visualizations using the diverse tools offered by Pandas. The df head function is often used in Pandas, a popular Python library for data manipulation and analysis, specifically designed for working with tabular data. This function allows you to see the initial rows of a data frame stored in the variable df. By default, it displays the first 5 rows, giving you a quick overview of the data's structure and contents. This can be helpful when dealing with extensive datasets, as it gives a brief snapshot of the data at the start, aiding in understanding the columns, values, and data types within the data frame. This enables the display of the dimensions of a data frame in Python. The output will be a tuple with the row and column count of the data frame. This method is practical for promptly verifying the size of the data frame, which is crucial for different data analysis activities. It assists in confirming the dataset's structure and guarantees the accuracy of the dimensions used in analysis. This method counts the number of missing values in each column of a Pandas data frame. The process involves using the df isNull function to create a new data frame where each cell is true if the original cell in the data frame was nan, null, and false if it was not. By applying the sum function to this Boolean data frame, it calculates the total count of true values in each column, which corresponds to the number of missing values in the original data frame. Detecting missing values in a dataset is a crucial step in data pre-processing for data analysis and machine learning purposes. Recognizing missing data helps in decision-making regarding data cleaning techniques, handling missing values before training machine learning models, and conducting further analysis. This snippet is utilized to generate a basic line plot displaying closing prices across time. The functionality is outlined below. 1. Initiates a figure and a subplot layout through PLT. Subplots method, with a single subplot in a 1x1 grid and sets the figure size to 10x10. 2. Selects the close, prices and date values from a DataFrame named df. 3. Configures a subplot using PLT. Subplot 212, displaying a grid via PLT. Grid true. 4. Designates labels for the x-axis and y-axis using PLT. X-label and PLT. Y-label. 5. Provides a title for the plot using PLT. Title. 6. Ultimately, plots the close prices against the DataFrame index and specifies the line color as green. This code segment is essential for visualizing the closing prices of stocks or financial data over a time frame, aiding in the analysis and interpretation of price trends and patterns through a graphical representation. This process involves the following steps. 1. Extract the close column from the DataFrame. 2. Convert the values in the close column to the float32 data type. 3. Reshape the resulting 1D array into a 2D array with a single column. 4. Store the reshaped 2D array in the variable closing_stock. This code readies the closing stock prices of a company for further examination or analysis by standardizing the data type and shape. This is beneficial for machine learning algorithms or mathematical operations requiring data in a specific format. Converting the data to float32 and reshaping it into a 2D array ensures consistency and compatibility with various data processing techniques and libraries. This indexing operation retrieves data from a numpy array named closing_stock. The syntax accesses all rows of the array, and 0 selects elements from the first column of those rows. In numpy, this type of indexing is employed to extract specific elements or segments of an array based on the specified indices. Here, 0 retrieves all rows but only the elements from the first column. This code is useful for extracting or working with data in the first column of the closing_stock array. By utilizing this code, you can manipulate, access, or perform operations specifically on the data in the first column while leaving the rest of the data unaffected. This explanation is about reshaping an array. 1. It selects the first column of a two-dimensional array called closing_stock and saves it as a variable named stocks. 2. The array stocks is reshaped using the reshape function, adjusting the shape to have the same number of rows as the original array's length, but with only one column. This kind of transformation is common when dealing with machine learning frameworks that require input data to be in a certain format. In simpler terms, this code takes the first column of the closing_stock array, altering its shape into a new structure where the number of columns is set to 1. This modification may be essential for preparing data for further analysis or processing, especially with machine learning algorithms that rely on specific input shapes. This text explains the min-max scaling technique used to scale the values of the stocks dataset. The steps involved in this technique are: 1. Import the min-max scalar class from the preprocessing module of scikit-learn. 2. Create a min-max scalar object named scalar with a feature range of 0, 1 to determine the scaling limits. 3. Use the fit_transform method of the min-max scalar object on the stocks dataset to fit the scalar to the data and transform it based on the specified scaling ranges. Min-max scaling is employed to normalize the dataset so that all features fall within a designated range, e.g., between 0 and 1. Scaling data before training a machine learning model is crucial to ensure all features contribute equally to the model, promoting efficient convergence during optimization. This scaling technique standardizes the range of independent variables, preventing any one feature from overshadowing others and improving overall model performance. This process splits a dataset into training and testing sets. Here's a breakdown of the steps. 1. Calculate the length of the stocks dataset. 2. Calculate 80% of the dataset's length and save it in the variable train to represent the training set size. 3. Calculate the testing set size by subtracting the training set size from the total dataset length, and store the result in the variable test. Splitting a dataset into training and testing sets helps in training a machine learning model using the training set and evaluating its performance on the testing set. This approach aids in understanding how well the model generalizes to new data and prevents overfitting. By creating distinct training and testing sets, we can accurately assess the model's performance. This snippet displays the variables train and test to examine the data they contain. Printing train and test allows us to verify the dataset split for machine learning models. It helps in observing the distribution of data between the training and testing sets to ensure the split is accurate. Developers can visually confirm the correctness of the segregation by examining the content of train and test and make necessary adjustments. This verification is important in supervised machine learning to ensure the model is trained on the right data and tested separately for performance evaluation. This snippet selects a subset of items from a list or array named stocks. The sublist is taken from the first element, index 0, up to the variable train, which likely indicates where to end the subset. For example, if stocks is 10, 20, 30, 40, 50, and train is set to 3, then train equals stocks 0. Train would choose elements from index 0 to index 2, resulting in 10, 20, 30. Such operations are common when splitting a dataset into training and testing sets to choose a portion for training. This code simplifies the extraction of a desired subset of data based on a specified boundary. This text describes slicing a list named stocks. It extracts a portion of the list, beginning from the length of another list named train and continuing to the end of the stocks list. This slicing is commonly used to isolate a segment of the stocks list for further analysis or testing. It is frequently applied in machine learning or data analysis to divide datasets into training and testing sets. By selecting a subset of the data after the training set, train, one can evaluate a model's performance or examine data that the model has not encountered during training. This technique aids in assessing how effectively the model generalizes to unfamiliar data. In summary, this method is vital for partitioning datasets and ensuring that the model performs well not just on the training data but also on new, unseen data. Reshaping the arrays train and test into a single column is achieved by using the reshape method, which modifies their shape without changing their data. This process is important when working with machine learning models that require data to be in a particular format, such as a specific number of features. Having a single column is often necessary when preparing data for algorithms that need a 2D input shape, as seen in scikit-learn. This snippet provides the dimensions, number of rows and columns, of two datasets, train, and test. The function shape in Python is utilized to retrieve the dimensions of a DataFrame. It yields a tuple with the first element denoting the number of rows and the second element denoting the number of columns. Displaying the dimensions of both the train and test datasets enables a rapid examination and juxtaposition of rows and columns in each dataset. This data is valuable for comprehending the data structure and pinpointing any variances or discrepancies between the training and test datasets. The function process_data prepares data for a machine learning model. It has two inputs: data, which is a numpy array containing the dataset, and n_features, an integer representing the number of features for prediction. Here's the process. 1. Initializes two lists, data X and data Y, to store input and output data for the model. 2. Iterates through the input data array from index 0 to len, data, n_features 1. 3. For each iteration I, it slices the input data array to extract a sub-array of length n_features from index I. 4. Appends the sub-array to data X. 5. Appends the next element in the data array after the sub-array is extracted from index I plus n_features to data Y. 6. Returns two numpy arrays, data X and data Y, as input and output for the machine learning model. This code is essential for preprocessing data before using it with machine learning algorithms like neural networks or regression models. It arranges the data into input-output pairs, making it suitable for supervised learning. The n_features parameter determines the number of time steps or features used for prediction, which is crucial for learning data patterns. The use of numpy arrays ensures efficient handling of data structures and computations needed for training the model. This segment describes a process in a machine learning workflow that involves data preparation for model training and testing as follows. 1. It initializes the variable n_features with the value 2, representing the number of features in the dataset. 2. The process_data function is invoked twice, once for the training data, train, and once for the testing data, test. 3. The process_data function is presumed to conduct preprocessing tasks on the raw data, train and test, such as feature engineering and normalization. This function separates input features, x, from the target variable, y, and returns the processed x and y for both training and testing datasets. 4. The function requires two inputs: the raw data, train and test, and the number of features, n_features. In essence, this code snippet readies the data for training and testing a machine learning model by processing it to comply with the desired input structure. It is standard practice to divide the data into training and testing sets, apply pre-processing steps, and ensure the model is trained effectively to recognize patterns and generalize well to new data. This snippet retrieves and prints the shapes of the training features, training labels, testing features, and testing labels. It is a common practice in machine learning projects to verify the dimensions of the input data before using it in a machine learning model. Understanding the shapes of the data arrays is essential for correct data pre-processing and model training. It guarantees that the input data aligns with the expected dimensions of the model, reducing errors related to dimension mismatches and facilitating debugging during the training phase. The arrays trainX and testX are being reshaped into a three-dimensional form by adding an extra dimension. This results in the arrays having the shape asterisk, number of samples, 1, number of features. This type of reshaping is commonly used in machine learning tasks, especially in deep learning models that require input data to be in a specific format. For instance, certain deep learning libraries expect input data to have a shape like asterisk, batch size, image height, image width, number of channels. Reshaping the arrays in this manner ensures that the data is in the correct format before it is fed into the model. This snippet imports modules necessary for building and training neural network models for time series forecasting. 1. The math module is imported to access mathematical functions. 2. The sequential class from Keras models allows creating models layer by layer. 3. Layers like dense, batch normalization, dropout, and activation can be added to neural network models. 4. LSTM and GRU layers, specialized for sequence prediction, are imported. 5. Optimizers like ADAM, SGD, and RMS-prop can be used while compiling neural network models. 6. The min-max scaler from scikit-learn is imported for scaling feature values within a specified range. 7. The mean_squared_error function from scikit-learn is imported to evaluate regression model performance. Overall, these imports provide the necessary tools to create, train, and evaluate neural network models for time series forecasting. Callbacks in a neural network training process using the keras library are functions that can be applied at different stages, such as at the end of an epoch. They help in tasks like adjusting the learning rate, saving the model, or stopping training early based on certain conditions. 1. Reduce LR on plateau callback reduces the learning rate when a metric stops improving. It monitors the validation loss, reduces the learning rate by a factor of 0.1 when triggered, and has a patience of 1 epoch. 2. Model checkpoint callback saves the model weights during training. It saves the model weights to the specified file path when the validation loss achieves the best value. Utilizing callbacks like these enhances the neural network model's performance during training by adjusting learning rates dynamically and keeping track of the best model parameters. It also offers features to save the model's progress, essential for resuming training or comparing models later. This neural network model is defined using the keras library with the TensorFlow backend. Here's an overview of its components. 1. A sequential model is created, representing a linear stack of layers. 2. The model begins with a GRU layer with 512 units and an input shape of 1, n_ features. The GRU layer is configured to return full sequences of output. 3. A dropout layer with a 40% dropout rate is added after the GRU layer to aid in regularization by randomly setting input units to 0 during training. 4. An LSTM layer with 512 units, capable of learning long-term dependencies, follows the dropout layer. 5. Another dropout layer with a 40% dropout rate is added after the LSTM layer for further regularization. 6. A dense layer with 128 units and ReLU activation function is incorporated to introduce non-linearity and facilitate learning complex patterns. 7. Finally, a dense output layer with 1 unit is added without an activation function for regression tasks. The model's architecture, layer types, output shapes, and parameter counts can be viewed by calling the model summary function. This deep learning model combines GRU and LSTM layers with dropout regularization to prevent overfitting while leveraging dense layers with activation functions to learn intricate data patterns and make predictions. The model summary output provides valuable insights into the model's structure, aiding in understanding the architecture and addressing potential issues. This text describes compiling a neural network model in Python using TensorFlow or keras library. The mean_squared_error loss function is defined to calculate the mean squared error between the model's predictions and the target values during training, aiming to minimize this error. The optimizer atom LR equals 0.0005 is set to update the neural network weights during training. It uses the atom optimizer with a learning rate of 0.0005, which dynamically adjusts the learning rate for each parameter. The evaluation metric, mean_squared_error, is specified to monitor the model's performance during training by calculating the mean squared error between the model's predictions and the target values. Compiling the model is crucial before training as it configures the model for training by setting the loss function, optimizer, and evaluation metrics. This prepares the model for training a neural network for regression tasks with mean squared error as the loss function. This text describes the process of training a machine learning model with specified parameters, using training data trainx and trainee for 100 epochs with a batch size of 32. The training process includes the use of callbacks like checkpoint and LR_reduce. The model's performance is evaluated on validation data testX and testY. Here is a breakdown of each component. trainX and trainee are used as input features and target labels for training the model. Setting epochs equals 100 determines how many times the model will be trained on the entire dataset. Setting batch_size equals 32 controls the number of samples used in each iteration for updating the model's weights. The callbacks checkpoint and LR_reduce are functions applied during training, such as saving the best model weights and adjusting the learning rate. Validation_data equals testY is the data used to evaluate the model's performance during training. Using this approach aids in the efficient training of a machine learning model by defining training parameters, incorporating callbacks for additional functionalities, and assessing the model's performance to avoid overfitting. It streamlines tasks like saving the best model, adjusting the learning rate dynamically, and monitoring the model's performance on unseen data. The visualization below illustrates the training progress of a machine learning model using matplotlib. 1. In the first section, two sets of plot commands show mean-squared error values for the training set, mean_squared_error, and the validation set, val_mean_squared_error, over training epochs. The plot's title is set to model mean-squared error. The y-axis label is accuracy. The x-axis label is epoch. A legend is added to differentiate between datasets. The graph is displayed using plt show. 2. In the second section, another pair of plot commands demonstrate loss values, a minimized function like mean-squared error, cross-entropy, etc., for both the training, loss, and validation, val_loss, sets across epochs. The plot's title is model loss. The y-axis label is loss. The x-axis label is epoch. A legend is included to distinguish between datasets. The loss graph is then displayed. These plots are essential for monitoring the machine learning model's performance and progression during training. They help visualize how well the model learns from the training data and generalizes to unseen validation data. Observing these graphs can offer insights into issues like overfitting, underfitting, and model convergence problems, enabling adjustments to the training process. This function, named model_score, evaluates a given model on training and testing datasets by using mean-squared error, MSE, and root mean-squared error, RMSE, metrics. 1. It calculates and prints the MSE and RMSE for the model's performance on the training data. 2. It calculates and prints the MSE and RMSE for the model's performance on the testing data. 3. Finally, it returns the MSE for both the training and testing sets. The main goal of this function is to analyze how well a machine learning model fits the data by studying its performance on training and testing datasets. This evaluation aids in fine-tuning model hyperparameters, identifying potential issues with the training process, and assessing how well the model generalizes to unseen data. This process involves taking the testing data testX, making predictions with the given model, and then reverting the predictions back to their original scale using a scaler. This transformation is important to present the predictions in a more easily understandable and comparable form. It is essential to use this code to interpret the model's predictions effectively. While scaling helps normalize the data and enhance the model's accuracy, undoing the scaling is useful for interpreting the final results and obtaining predictions in their original units. To quickly evaluate the model's performance on the test data, the code displays the first 10 predictions, pred. 10. This allows for a brief assessment without overwhelming the user with the entire array of predictions. This snippet executes the following operations. 1. Converts the array testY into a column vector. 2. Utilizes a scalar object to reverse the transformation of values in the array. 3. Displays the first 10 elements of the array testY. Reshaping testY into a column vector is crucial for compatibility with certain machine learning libraries and models that demand the target variable to be in a specific shape. This ensures that the data meets the expected format for these models. The inverse transformation using the scalar object is typically applied to revert normalized or scaled values to their original scale. This step is important when making predictions or assessing the model's performance in the original datascale. In essence, this code snippet is beneficial for preprocessing the target variable before deploying it in a machine learning model or evaluating the model's effectiveness. This snippet visualizes the actual and predicted prices of a certain asset over time. It adjusts the figure size, plots actual prices in red and predicted prices in green on the same graph, labels the axes, adds a plot title, includes a legend to differentiate between the two, adds a grid for readability, and displays the plot. This visualization is crucial for assessing the performance and accuracy of a predictive model, especially with time series or chronologically ordered data. Comparing actual and predicted prices on a graph allows easy identification of patterns, trends, discrepancies, and the overall effectiveness of the model. It aids in evaluating model performance and making informed decisions based on the comparison of actual and predicted values. Slicing in Python is demonstrated in this example. It shows how to extract elements from the list testY using slicing. The expression 10 is a slicing technique that retrieves elements from the 10th position from the end of testY to the end of the list. Slicing is a versatile feature in Python that enables working with subsets of iterables such as lists, tuples, and strings without altering the original data. It is beneficial for accessing specific element ranges and creating shallow copies of parts of the original data structure. Negative slicing in Python is a technique used to access elements in a sequence, such as a list or a string, starting from the end of the sequence. In the example provided, pred. 10 attempts to retrieve elements from the 10th element counting from the end of the sequence pred. When utilizing negative indices, -1 corresponds to the last element, -2 to the second to last element, and so forth. If pred is a sequence, pred. 10 will produce a new sequence containing elements from the 10th element from the end to the final element of the original sequence. This method is beneficial when you need to access elements from the end of a sequence without knowing the sequence's exact length. It's crucial to confirm that the sequence has a minimum of 10 elements for this slicing operation to execute without raising an index error. In essence, pred. 10 is employed to extract elements starting from the 10th element from the end up to the last element of a sequence, leveraging negative slicing in Python to streamline this process.